Hello, everyone. Welcome to part 6 in our series on supervised sentiment analysis. This screencast is going to cover two important methods in this space: hyperparameter search and classifier comparison. So let's begin with hyperparameter search. And first, I'll just offer the rationale. Let's say that the parameters of a model are those whose values are learned as part of optimizing the model itself. So for the classifiers we've been studying, the parameters are really just the weights that you learn on each of the individual features. And those are the things that are directly targeted by the optimization process. The parameters of a model are typically pretty crisply defined because they kind of follow from the structure mathematically of the model under investigation. Much more diffuse are the hyperparameters. We can say the hyperparameters of a model are any settings that are outside of the optimization process mentioned in 1. So examples from models we've seen are GLOVE and LSA have that dimensionality setting. The model itself gives you no guidance about what to choose for the dimensionality, and the dimensionality is not selected as part of the optimization of the model itself. You have to choose it via some external mechanism, making it a hyperparameter. And GLOVE actually has 2 other additional prominent hyperparameters, X, max, and alpha. Again, those are not optimized by the model. You have to select them via some external mechanism. And for the classifiers that we've been studying, we have regularization terms. Those are classic hyperparameters. If you have a deep classifier, then the hidden dimensionalities in the model could also be considered hyperparameters. Learning rates, any core feature of the optimization method itself could be considered hyperparameters. And even things that might be considered kind of architectural, like the activation function in the deep classifier, you might think of it as kind of an intrinsic part of the model that you're evaluating. But since it's an easy choice point for us at this point, you'll be tempted to explore a few different options for that particular architectural choice. And in that way, it could become a hyperparameter. And at this point, even the optimization methods could also emerge as a hyperparameter that you would like to do search over. And so forth and so on. You should probably take a fairly expansive view of what the hyperparameters of your model are if you can. Now, here's the crux of the argument. Hyperparameter optimization is crucial to building a persuasive argument. Fundamentally, for any kind of comparison we make, we want to put every model in its very best light. We could take it for granted that for any sufficiently complicated model, there's some setting of its hyperparameters that's kind of degenerate and would make the model look very bad. And so you certainly wouldn't want to do any comparisons against that really problematic set of choices. Rather, what we want to do is say, let's put all the models in their best light by choosing optimal hyperparameters for them to the best of our ability. And then we can say that one model is better than the other if it emerges victorious in that very rigorous setting. And the final thing I'll say about this methodologically is that, of course, all hyperparameter tuning must be done only on train and development data. You can consider that all fair game in terms of using it however you want to choose the optimal hyperparameters. But once that choice is set, it is fixed. And those are the parameters that you use at test time. And that is the fundamental evaluation that you would use for any kind of model comparison. And at no point should you be tuning these hyperparameters on the test data itself. That would be completely illegitimate. I hope we've made it really easy to do this kind of hyperparameter search in the context of the work you're doing for supervised sentiment analysis. Here are some code snippets that show how that can happen. I load in my libraries. I have a pointer to our sentiment data. And here I have a fixed feature function, which is just a unigrams feature function. The change happens inside the model wrapper. Whereas before, essentially, all we did is set up a logistic regression model and then call its fit method. Here, we set up that model, but also establish a grid of hyperparameters. These are different choice points for this logistic regression model, like whether or not I have a bias term, the value of the regularization parameter, and even the algorithm used for regularization itself, L1 or L2. The model will explore the full grid of these options. It's going to do 5-fold cross-validation, so test one each 5 times on different splits of the data. And in that very long search process, it will find what it takes to be the best setting of all of these hyperparameters, of all the combinations that can logically be set. And that is the model that we finally return here, right? So now you can see the value of having a wrapper around these fit methods, because then I could do all of this extra work without changing the interface to SST experiment at all. The experiments look just as they did in the previous mode, It's just that they will take a lot longer because you are running dozens and dozens of experiments as part of this exhaustive search of all the possible settings. Okay, part 2 is classifier comparison. And let's again begin with the rationale. Suppose you've assessed a baseline model B and your favored model M, and your chosen assessment metric favors M, right? And this seems like a little victory for you, but you should still ask yourself, is M really better, right? Now, if the difference between B and M is clearly of practical significance, then you might not need to do anything beyond presenting the numbers, right? If each one of your classification decisions corresponds to something really important in the world, and your classifier makes thousands more good predictions than the other model, that might be enough for the argument. But even in that situation, you might ask whether there's variation in how these two models B and M perform. Did you just get lucky when you saw what looked like a practical difference, and with minor changes to the initialization or something, you would see very different outcomes? If the answer is possibly yes, then you might still want to do some kind of classifier comparison. Now, there's this nice paper by Demschar, 2006, that advises using the Wilcoxon signed rank test for situations in which you can afford to repeatedly assess your two models B and M on different train test splits, right? And we'll talk later in the term about the precise rationale for this, but the idea is just that you would do a lot of experiments on slightly different views of your data, and it kind of average across them to get a sense for how the two models compare with each other. In situations where you can't repeatedly assess B and M, McNemar's test is a reasonable alternative. It operates on the confusion matrices produced by the two models, testing the null hypothesis that the two models have the same error rate. The reason you might opt for McNemar's test is, for example, if you're doing a deep learning experiment where all the models take a few weeks to optimize, then of course you can't probably afford to do dozens and dozens of experiments with each one. So you might be compelled to use McNemar's based on one single run of the two models. It's a much weaker argument because, of course, precisely the point is that we might see variation across different runs, and McNemar's is not really going to grapple with that in the way that the Wilcoxon sign rank test will. But this is arguably better than nothing in most situations, so you might default to McNemar's if the Wilcoxon is too expensive. And let me just show you how easy this can be in the context of our code base. So by way of illustration, what we're essentially going to do is compare logistic regression and naive Bayes. I encourage you, when you're doing these comparisons, to have only one point of variation. So we're going to fix the data and we're going to fix the feature function and compare only the model architectures. You could separately say, I'm going to have a single fixed model like logistic regression and explore a few different feature functions. But I would advise against exploring two different feature functions as combined with two different models, because when you observe differences in the end, you won't be sure whether that was caused by the model choice or by the feature function. So we want to kind of isolate these things and do systematic comparisons. So here I'm going to do a systematic comparison of logistic regression and naive Bayes on the SST using the Wilcoxon test. And here's the setup. The function is SST compare models. I point it to my training data. You can have two feature functions, but in that case, you should have just one model wrapper. Here I've got one feature function used for both models, and I'll have these two different wrappers corresponding to the evaluation that I want to do of those two model classes. I'm going to use the Wilcoxon as advised. I'll do 10 trials of each on the train size of 70% of the data. And as always in this setting, I'll use the macro F1 as my score. So what this will do internally is run 10 experiments on different train test splits for each one of these models. That gives us a score vector, 10 numbers for each model. And then what the Wilcoxon is doing is comparing assessing whether the means of those two score vectors are statistically significantly different. And here it looks like we have some evidence that we can reject the null hypothesis that these models are identical, which is presumably the argument that we were trying to build. Now, of course, that's very expensive because we had to run 20 experiments in this situation. And of course, you could run many more if you were also doing hyperparameter tuning as part of your experimental workflow. So in situations where you can't afford to do something that involves so many experiments, as I said, you could default to McNemar's. That is included in utils.mcnemar. And the return values of SST experiment will give you all the information you need. Essentially, for McNemar's, you need the actual gold vector of labels and then the two vectors of predictions for each one of your experiments. So that's a simple alternative in the situation in which Wilcoxon's was just too expensive.